back, everybody. What we're going to be doing today, this will be Friday, April 3rd. This is the Friday before Exam 2. So since, the first part of this material for Exam 2 is before spring break, and we've had a lot going on, and we've got this big split in between then and now, and we've covered material after spring break, I really wanted to kind of do a cohesive video that looks at all the topics for Exam 2, or at least most of the topics for Exam 2. Make sure that you understand a little bit of what's going on, and I want to practice a couple of things. This will help you put your best effort forward for this exam. A couple things to look at. Looking here, we've got a lot of people have turned in their CalcLab 2s. Make sure if you haven't done that, please get that into me as soon as possible. Also, at the end of today, this is on Friday, Quiz 8 is due. Quiz 8 is over related rates, problems, and rates of change. So hopefully you've finished that. Things that are coming up, do not forget you have a CalcLab 2 discussion. So a CalcLab 2 discussion where you go in, respond to the project, just like we did for CalcLab 1. That is due Monday at 8 a.m. Make sure you work on that this weekend if you haven't done it already. And then, of course, we have our exam coming up Monday. It says due at 11:59, but I want to talk about that to get started with today. Under the announcements, if you haven't seen it already, there is instructions for Exam 2. So this clearly outlines all the instructions, all the things you need to know for Exam 2. And then all of the notes and things like that, including the practice exam, can be found at this link. So if you follow this link over, here's your practice exam with an answer key, and then these are all the topics which are on the exam. So if I go back real quick, when you find 3 hours of time on Monday to take the exam, it is a timed exam. From the moment you start it, you will have 3 hours to finish it. When you're ready to begin the exam, click on this link. That'll take you to the Exam 2 assignment. That'll take you to this Exam 2 assignment. It is unlocked because I'm in teacher mode, but for you guys right now, it'll say this won't be unlocked if you go there before Monday. But once you start it on Monday, you only have 3 hours to finish it. So find you a block of 3 hours and work on it. There are some special instructions. For example, you can have a sheet of notes with you, but you're not supposed to use your book or any online resources, but I will let you have a sheet of notes that you could put formulas, hints, reminders, etc. on, and then I'll ask that you upload that as well as some other questions during the exam. So take a look at this. If you have any questions about it or if there's something you don't understand about it, let me know. What I want to focus on in this video is the actual material itself. So let's take a look at material for Exam 2. First off, some topics to consider. One of the big things, which is I'm not actually going over on this review because I had to pick and choose, is derivative sketching and matching. There's some problems in section 2.8 that we did about a week, maybe even 2 weeks before spring break that this fits. And these are those problems where, say you have multiple functions and you're asked to pick which is the first derivative, second derivative, third derivative, right? So you can pick, can you pick f prime, f double prime for a given function f of x? That's definitely going to be something that you want to look out for. It's something that you may have forgotten is on this exam because it is back in Chapter 2, but it's one of the last things we did in Chapter 2. Another thing that's kind of like that you may have forgotten is interpreting the derivative. So this is mostly stuff out of section 3.7, the dealing with rates of change. But it's things like units, like what are the units of a derivative? It's things like what does it mean if I tell you that c prime of 30 is negative 150 where c is a cost function? What does that mean? Well, that means the expected cost decrease from x equal 30 to x equal 31 is about $150. Oops. Right, so things like that. Things that are word problem associated, derivative kinds of problems dealing with rates of change in units. You've also got the position, velocity, acceleration kinds of questions that are a part of that section 3.7 stuff. That's a big part of the exam. I'm going to go over position, velocity, acceleration example with you in this video, but that's going to be a big part of this exam. Another big part of the exam, and probably the biggest part, this is the exam where you prove to me, or maybe prove to yourself, that you can calculate derivatives, right? We've gone over power rule, chain rule, product rule, quotient rule. Goodness, we've done exponentials, logs, logarithmic, implicit. All these different kinds of derivative formulas, those are on this exam. So make sure that you go back and take a look at those things and that you can calculate the derivative of a function that I give you. The other thing I'll say is calculating tangent lines. There are 3 different ways that we've done this. Calculating the tangent line of a function at a point xy. Calculating the tangent line of an implicit function at a point xy. And then in the Calc Lab, I told you this would be on the exam, calculating the tangent line to a parametric curve at a given point x and y. And I'm going to do an example of these two in today's review. The first one was more like something you did on test 1, but we've calculated tangent lines and normal lines to each of these curves in class. We've done examples of those. Then you have, your related rates problems. Definitely going to have one of those on the exam. There's going to be some true, false, multiple choice over things like definition of what it means to be differentiable. Does differentiability implies continuity? Remember, we had a theorem that we proved together about all that. Those kinds of things are also a part of this test, understanding the relationship between differentiability and continuity. Honestly, those are the main things. As I'm sitting here just thinking about what's on the exam, those are the main things for you to go back and look at. But remember, the practice exam and the practice exam page has a thorough listing of all the topics for this exam. All right. So let's just get started and look at some examples. I'm going to calculate some derivatives with you first because that is the heart and soul of this exam. And I'm going to do these kind of quick. You can pause it and stop anytime if I get ahead of you. But I'm just going to talk through it as I'm doing it, working it the way I normally would. All right, looking at this problem, I would look for this to be a chain rule. So the outer function is something to the fourth, so it's 4 times that thing cubed, but then I have to multiply by the inner function. And the inner function's derivative is 2x plus 3x squared. Distribute the 4 to those, and you'll have 8x plus 12x squared times this. And you cannot do any more algebra than that. You could factor out an x and a 4 or something like that here, but you can't distribute this into here. You can't distribute anything out of here. You're stuck. So that's as far as you would go. All right, so this problem clearly is going to require quotient rule. So quotient rule, my u is tangent. My u prime, then, the derivative of tangent is secant squared. You do need to know that. You are expected to know that. V is 1 plus cosine. So v prime, the derivative of 1 is 0. The derivative of cosine is negative sine. So the derivative here would be u prime v minus uv prime over v squared, which is secant squared times 1 plus cosine minus tangent times minus sine, I'm going to make that plus sine, over v squared, which is 1 plus cosine of x quantity squared. Now I don't see a really good way of simplifying this result, so I'm just going to leave it as is. Don't worry about simplifying unless there's easily something to pull out or cancel with the denominator. If you did want to take this term and cancel with the denominator, then you would need to separate out these two parts, but I would just leave it like this. All right, next up is this one. Don't be fooled by the way this looks. This is actually a little bit tricky here. This is the natural log of x times the natural log of x. Now, I put this problem on here specifically to remind you of something, and that is properties of the log can help you. If you have the natural log of a times b, that's the natural log of a plus the natural log of b. So for this example, I can think of this as being the natural log of x plus the natural log of the natural log of x. And I think that's going to be much easier to differentiate overall. So I'm going to let y be equal to that, in which case dy dx is the derivative of the first piece, which is natural log, plus the derivative of the second piece, which is the log of the log. So starting with the natural log, the derivative of log is 1 over x. You definitely need to know that. And the derivative of the natural log of a function, this is another formula that I'll remind you of. Natural log of a function is the derivative of the function divided by the function. That's always going to be the case. So that's the derivative of the log. So the derivative of a logarithm of something is the derivative of that thing over that thing. So in this case, we've got the inner function is log, so I'm dividing by log, but the inner function's derivative, right, the derivative of natural log x is 1 over x. That's my f prime of x, so I'm going to place it in top like this. And so we get 1 over x plus 1 over x ln x. And so that's a really good answer for this problem. All right, another example. Here we have an implicit function. Because of the cosine of y here, there's not a good way to write this as y equal a function of x. So I have to treat y as though it's a function of x, and then use chain rule. Anytime I take the derivative of a y term, I have to multiply by dy dx. So we'll start by taking the derivative of both sides. All right, so here I've distributed the derivative to each piece. So the derivative of y is dy dx, and the derivative of this piece. And then over here, the derivative of this piece. Now, you're going to have to be very careful here because this is product rule, because it's x times cosine of y. Y is a function of x. So it's a function of x times a function of x, and it's the same thing here. I'm going to use product rule on both pieces. So this is dy dx plus the derivative of x is 1 times cosine y plus x times the derivative of cosine is minus sine. So I'm going to change this to a minus. So it'll be minus sine of y, but then I just took the derivative of a y, so I have to multiply by y prime. Okay, on the right-hand side, product rule. The derivative of x squared is 2x. The derivative of y is y prime, or dy dx. And so there is the correct derivative taken on both sides. To finish out this problem, you should solve for dy dx. So I'm going to bring all my dy dx's over to the left. So dy dx minus x sine y dy dx. Then bring this other one over, so minus x squared dy dx. All of the other terms are on the other side, so this is 2xy minus cosine y. And then finally factor out the dy dx. And finally, divide that term over. So the algebra is usually the trickiest part of these problems, but this is the methodology behind solving a problem where you're having to differentiate implicitly. You take the derivative of both sides, treat y as a function of x. Anytime you take the derivative of y, like I did here, the derivative of cosine is minus sine, you have to multiply by the derivative of the y term. The derivative of y here is just dy dx. So I used product rule both here and here. Okay, next up is the square root of secant. This is a chain rule problem. My outer function is the square root, my inner function is secant. So the derivative of the square root of secant, so the outer function is 1 over 2 times square root secant. That's how you differentiate a square root. Remember, the derivative of the square root is 1 over 2 times whatever's inside it, right? So if there's a secant inside it, it's 1 over 2 times the square root of secant, like we have here. But then because there was secant inside of it, I have to multiply by the derivative of secant. So I don't know if you recall or not, but the derivative of secant is secant tangent. So secant tangent over 2 square root secant. And if you wanted to, you could take secant to the 1, secant to the 1/2. 1 minus 1/2 is 1/2. So you could rewrite all of this as this if you like. So that would be the best form of the answer there. Okay, that's just a chain rule. So that's a chain rule example. Okay, here we have an exponential. Remember, this is the simplest they can possibly be, right? The derivative of an exponential is itself. If you have a base other than e, say a to the x, then the derivative is natural log of a times a to the x. But here our base is e, so this is pretty simple. If I take the derivative of both sides, I do the outer derivative first, so it's e to something. So the outer derivative of that is e to that thing. But then I have to multiply by the inner derivative, which is going to involve product rule. So come over here to the side, my u is x, so u prime is 1. My v is sine, so v prime is cosine. And so u prime v plus uv prime is what we would have, which would be 1 times sine plus x times cosine. So this derivative is sine plus x times cosine. And so that's all there is to it. I know this piece requires product rule, so I used product rule to finish it out. The piece right here, going from here to here, I used chain rule. So this is a problem that has a product rule inside of a chain rule. You have to be able to work with multiple rules in a single problem. All right, number 7. So I see something to the -4, so I'm thinking chain rule, and I'll have to multiply by the derivative of the inner part here. So dy dx equals the derivative of this. So this is negative 4 times this to the, remember you subtract 1 from the power. So this would actually be negative 5. But then I have to multiply by the derivative of the inner function. Okay, so if I come over here to the side, the derivative of 1 is 0. The derivative of negative 2 over x is negative 2. You got to be careful here. So this is the same thing, just to make sure you're aware. This is the same thing as the derivative of negative 2x to the negative 1, right? Because you're dividing by x. So power rule says the derivative of that would be negative 2 times negative 1x to the minus 2, which is 2x to the negative 2, or 2 over x squared. So this would be negative 4, 1 minus 2 over x to the negative 5, times the derivative is 0 plus 2 over x squared, so 2 over x squared, which would be negative 8 over x squared. And then remember, so x squared's in the denominator here. You've got a negative 8 in the numerator. This negative 5 means this term is actually in the denominator. So I'm going to write this in the denominator, and I think that's probably the best way to write the answer overall for this problem. So just remembering things about exponents and the way they work. Remember our power rule says this, and we know that n can be any real number, which means that, for example, x to the, so like the cube root of x to the 5th. We know that's the same thing as x to the 5/3. So the derivative is 5/3 x to the subtract 1 from the power. So subtracting 1 from 5/3 gives you 2/3. It can handle roots, it can handle reciprocals. So power rule, incredibly important on this test. All right, looks like we have another implicit one here. So we're going to treat y as a function of x. Take the derivative of both sides. So the derivative of this first piece is going to involve product rule. The derivative of the other side is pretty simple. So here we take, well, you can do u is x, u prime is 1, v is e to the y, which means v prime is e to the y times y prime. So on the left-hand side, you would have u prime times v, so u prime times v plus u times v prime, and on the right-hand side, the derivative of y is y prime, the derivative of negative 1 is 0. So I need to solve for y prime. So algebraically, I'm just going to leave the e to the y on the left, and I'm going to bring this term over to the right. I can factor out a y prime from that term on the right. And so y prime would be e to the y divided by this term. Okay, finally, our last derivative example, taking more than one derivative, just to make sure y'all are aware of that. So if you took the first derivative here, it's not too bad. So this would be f prime of t. So this derivative would be 1 over 2 times the square root of this function. But then you'd have to multiply by the inner derivative because of chain rule. So the inner derivative there is 4. So the 4 and the 2 would cancel, leaving a 2. So there is your first derivative. So that's f prime. which means that f double prime would be taking the derivative of the derivative. Okay, that's not too bad here. So if we take this again, I want to look at this function using power rule. This is 2 times 4t plus 1. This is a square root in the denominator. So the power for that is negative 1/2. So chain rule says that this would be 2 times negative 1/2 times 4t plus 1 to the subtract 1 from the power. So it would now be minus 3/2. But then I have to multiply by the inner derivative, which we know from up here is also 4. So 2 times negative 1/2 is negative 1, but then I have to also multiply by 4. So let's just do negative 4 times 4t plus 1 to the negative 3/2. So this gives 4, which then multiplies those three together. So you have 2 times negative 1/2, which is negative 1, negative 1 times 4, which is negative 4. So your second derivative is negative 4 over 4t plus 1 to the 3/2. So the second derivative evaluated at 2, which is what this is asking me to do, is just replace the t with 2. So this would be negative 4 over, let's see, 4t, 4 times 2 would be 8, plus 1 would be 9. So this is 9 to the 3/2. So if you remember how this works, the number on top is the power, the number on bottom is the root. They can be done in any order. So you can do the power first or the root first, whichever one's more convenient. Here it's more convenient to do the root first. So the square root, since 2 is the root, the square root of 9 is 3, then 3 cubed is 27. So this number on bottom would be 27. All right, so you are going to be responsible for finding derivatives at points, and you could be asked to do, 2 derivatives like this. Another kind of question that we dealt with was functions of x raised to functions of x. So this kind of problem is f of x raised to the g of x, where f of x and g of x are functions of x. And so I have to think about how to do this, and the only way to do these problems, if you recall, is with something called logarithmic differentiation. So the way that logarithmic differentiation works is you take the natural log of both sides, and then once you've taken the natural log of both sides, you use properties of the log to make the right-hand side more appropriate to take a derivative of. For instance, the property of the log that's important here is if you have the natural log of a to the b, that's b times the natural log of a. So the x inside comes out, and now this is not too bad to do. I can now take the derivative of both sides with respect to x. On the left-hand side, the derivative of natural log of y is y prime over y. And on the right, this is the natural log, oh, I forgot my x. This is the x times the natural log of cosine of x. So this is product rule. I've got a function of x times another function of x. So I'm going to use product rule here, the derivative of the first times the second, plus the first times the derivative of the second. Now the derivative of this term is a little tricky. It's over cosine since it's a natural log, but then I have to multiply by the derivative of the thing that's inside. The derivative of cosine is minus sine. So this is y prime equals, multiply the y over to finish this out. Natural log of cosine. This sine over cosine is tangent, so you could write this as minus x times tangent. And then your final answer, you should replace the y with what it originally was. So the best answer here is cosine of x to the x times all of this. So this is a technique known as logarithmic differentiation. It is the only way that we have to differentiate functions of this form. A function of x whose exponent is also a function of x. All right. So next problem. We had problems very similar to this in class, even before the break, where I had a table of values and then you had to calculate the derivative at different values. So I'll do this using the Newton notation here. So s prime at 1 would be f prime at 1 plus 3g prime at 1. Remember how the derivative, if you differentiate s, then you differentiate both of these as well, so it distributes to both. And we're going to evaluate both at 1. And then according to the information given, f prime at 1 is 3, g prime at 1 is 1, so this is 6. Okay, here you've got a function of x times another function of x, so when I take the derivative of this, I've got to use product rule. So p prime of 2 would be f prime of 2 g of 2 plus f of 2 g prime of 2. And so the information provided tells us this is 2 times 1. F at 2 is 1. G prime of 2 is 4. So this looks like 2 plus 4, or, once again, 6. Let me just double check that. F prime of 2 is 2. G of 2 is 1. F of 2. Yep, that looks right. All right, so here we have a quotient. This is the f divided by g. So I'm going to have to use quotient rule here. So q prime of 1 would be f prime of 1, g of 1, minus, right? Product rule is plus, quotient rule is minus f at 1, g prime at 1, all over g at 1 squared. So it's the same values as what we have right here, it's just subtracting them. So it's 2 times 1 minus 1 times 4 divided by g at 1. Let's see, g at 1 is 3. Oh, actually it's not the same values because this is at 1, not at 2, like the problem above is. So I'm going to have to look at each one of these individually. All right, so f prime of 1 is 3. G at 1 is 3. F of 1 is 2. And G prime of 1 is 1. G of 1 is 3, so it's over 3 squared. So it would be 9 minus 2 over 9, or 7/9. Okay, finally, this is chain rule. It's f of g. So c prime at 2 would be f prime, that's the outer function's derivative first, multiplied by the inner function's derivative, and all of that evaluated at 2. So, this page, this problem, it's really just about you knowing these formulas. It's about you knowing the properties of the derivative, product rule, quotient rule, chain rule, the derivative distributes, how to work with the notations. It's all very important that this should seem easy to you. This stuff right here is just mainly notational stuff. So f prime of g of 2, okay, let's look. G of 2 is 1 times g prime of 2. So f prime at 1 is 3. G prime of 2 is 4. So this is 12. So you need to be prepared for problems like this that ask you to calculate the derivative at a point. Remember, it's possible with chain rule. So even though we were evaluating the derivative at 2, we had to evaluate this function at 1. Remember, it's possible for these problems to be asked to evaluate the derivative at a point you don't have information for. So as far as the chain rule is concerned, you can occasionally get problems where you cannot determine the value because you're not given enough information. All right, tangent lines. So I want to find a tangent line to this curve at the point 2, 1, and it's assumed that the point is xy equal to 2, 1. So I have to first find my slope implicitly by taking the derivative of both sides. So on the left-hand side, the derivative is 2x plus the xy term here is product rule. So this will be 4y plus 4xy prime plus 2y, so the y squared term, the derivative of 2y, or the derivative of y squared is 2y times y prime equals, on this side, distribute the derivative to 13, the derivative of 13, since it's a constant, the derivative is 0. And rather than solving for y prime at this point, plug in the values you have. You know that x is 2, you know that y is 1, so plugging in those values, x is 2, y is 1. Y prime is unknown, it's what we're going to want to solve for. Okay, so this is 4 plus 4 is 8, plus 4 times 2 is 8, plus 2y prime. So 10y prime is negative 8, or y prime is negative 8/10, or negative 4/5. So this is my slope, and this is my point. So when it comes time to look at the tangent line is y minus, the y value here is 1, equals the slope times x minus 1. And the normal line, if you recall, is the line that's perpendicular to the tangent line. So it would be y minus 1 equal to the perpendicular slope. So if negative 4/5 is the slope of the tangent, remember the slope that's perpendicular to that. So this is perpendicular to the tangent line. The slope that's perpendicular to the tangent line would be positive 5/4. It would be the negative reciprocal of that one. So this would be the normal line to the curve at that point. All right, definitely gonna have to do these. We did these on a quiz earlier, so make sure that you're aware of that. Okay, next we have a parametric curve. This is like what you did on the Calc Lab. So can I find the line tangent to this parametric curve? So my x coordinate varies as t squared, and my y coordinate varies over time as t squared minus 4 sine t. I'm asked to find tangent at the point pi squared 0. Once again, this is x and y. So when x is pi squared and when y is 0, I want to figure out what the tangent line is at that point. So once again, it's just like up here, it's just we have a different way of finding the slope. I'm going to have to find the slope first, then I have a point, but let's find the slope first. So to find the slope here, which is dy dx, because it's parametric, I have to take dy dt and divide by dx dt. So the derivative of y with respect to x, that's going to involve product rule. So let's do that real quick. This would be, let's see, that's what, 2t sine t plus, right, because I'm doing u is t squared minus 4, so u prime is 2t, and v is sine t, so v prime is cosine t. So u prime v plus u v prime. Divided by dx dt, which is the derivative of t squared, which is 2t. So this is just sine t plus t squared minus 4 over t over 2t, I believe. Yes. Times cosine of t. So took this term divided by there, the two t's canceled out, leaving just sine t squared minus 4 over 2t. The term there canceled out, leaving cosine. Okay, so this is my slope, but it's as a function of t. I know x and y, the point at which I'm supposed to evaluate this, but I don't know at what time these occur. So when is x equal to pi squared or y equal to 0? That's what I need to know. Well, if you look, x is t squared, so if t is pi, then it would kind of make sense that this would be right. So t equal to pi makes sense. But understand that it could also be negative pi. Right? So when is x equal to t squared? Well, if t is pi or t is negative pi, that could be the case. Okay, what about then y equal to 0? Well, if you look at y is t squared minus 4 sine t. So all the places where this could be 0, from this first piece, t squared minus 4 equals 0. Well, this is a difference of squares. So it could be 0 at t equal to 2 or negative 2. And then sine is 0 when? Well, sine is 0 when t is equal to 0 plus or minus pi plus or minus 2 pi and so on. And what you do is you look at all the places where x is satisfied for t, all the places where y is satisfied for t, and see if there are any overlaps. If there are any overlaps, then those are points in time where you visited the point pi squared 0 in this case. So you can see that there is an overlap here. At pi and negative pi, pi and negative pi, both x and y are the required values. Okay, so I have to check my slope at time pi and at time negative pi. So first off, the slope at time pi would be, so I'm plugging pi, this is my slope formula here. I'm plugging pi into this, sine of pi is 0, cosine of pi is 1. I would have pi squared minus 4 over 2 pi. Okay? And then, so that's my first slope. And then my second slope is at negative pi. And if I plug negative pi in, sine of negative pi is also 0. This is still pi squared minus 4. Cosine of negative pi would be negative 1. So cosine of negative pi would be negative 1. So you have, let's see, pi squared minus 4 over negative 2 pi. But then you have cosine of negative pi, and cosine of negative pi is negative 1. So I believe you get the exact same value here as here. So both of those have the same slope. You're just at that point at two different times. So the slope is the same in both cases. I think this is easier to stomach if you actually see it in Desmos. So let me pull this up in Desmos real quick. We'll bring that to one side and this to one side so we can look back at it. Okay. All right, so in Desmos, the way you do parametric equations is you list them as a coordinate. So our coordinate here is t squared, and then the y is t squared minus 4 times sine t. So t squared, and then t squared minus 4 times sine t. I don't have a time interval for this, but I know because this is pi and minus pi, I need to go out at least that far. So I'm going to do minus 2 pi to 2 pi. All right, so here is what our curve looks like. And we are asked to look at the point pi squared 0. So we're asked to look at this point. Okay, what's going on here is that we have, for these particular problems, one of these points gives one slope, the other gives the other slope, the negative of it. You can see here, if I pass through one time, I'm passing through going up when I pass through the point, and the other time I pass through the point, I'm going either down or to the left, right? So I've got a negative slope in this direction and a positive slope in this direction. We know from virtue, by virtue of the fact that we've done this, that this one is the negative slope, right? Because if I plug in cosine of pi is -1, so I have the negative slope at time pi, and I have the positive slope at time negative pi. So let's just put in the excuse me. Let's just put in the tangent lines. They would be y minus, the y value here is 0. The first slope is pi squared minus 4 divided by -2 pi times x minus pi squared. So you can see that looks really good. That's the slope at time pi. That's our tangent line to that point at time pi. Similarly, I could go in and copy and paste the same thing down and instead make it positive 2 pi, and you could see that that's the tangent line at time negative pi going in the other direction. So you are responsible for knowing how to differentiate, in other words, dy dx, take the derivative at a point on a parametric curve, as well as be able to find tangent lines at points. And one of the interesting things about parametric curves and implicit curves is they can have multiple slopes at a single point. That's not something that we dealt with regular functions. So you have to be aware of that for implicit curves and especially for parametric curves like this. I just thought this would be a good example to go over. I know you've gone over these in the Calc Lab, but it doesn't hurt to remind you of the fact that these are on the exam. All right, next question. Doing applied problems like particle motion, cost profit. This is a position, acceleration, velocity kind of question. So our position function is given by t cubed minus 12t plus 3 for t greater than or equal to 0. So I'm going to start by finding the velocity. So the velocity is the derivative of position, so it would be 3t squared minus 12. The acceleration would then be the derivative of that, so it would be 6t. Okay, when is the particle moving up? So moving up implies the velocity is greater than 0. Moving down implies the velocity is less than 0. So it's good to go in and do these what I call number lines for each of these. So we'll look at acceleration, we'll look at velocity. Acceleration, if t is positive, we're looking at t greater than or equal to 0. If t is greater than or equal to 0, the acceleration is always positive here. So it's if this is the acceleration graph, its acceleration is 0 at time 0, but everywhere else it has a positive acceleration. This one's a little bit more tricky. It's 3t squared minus 12, which would be equal to 0. If you look here, 3t squared minus 12 equals 0 when t squared is equal to 4. And so that would mean t is plus or minus 2. Those are times where the velocity is 0. We're once again only interested in this for positive times, so only t equal to 2 matters here. So I'll just say this is t equal to 2. So I need to test points. I know at time 0, if I plug t equal to 0 in, I get negative 12. So I have a negative velocity initially, 0 velocity at time 2. There's nothing to change it, so I know it'll be negative in here. Let's test a point to the right of t equal to 2, say t equal to 3. If I plug 3 in to the velocity, 3 squared is 9, times 3 is 27, minus 12 is 15, so that is positive over here. So this is just sort of a sign chart for acceleration and velocity. Okay, so when is velocity positive? Well, velocity is positive, or the particle is moving up for values of t greater than 2. And it is moving down. In other words, the velocity is negative from 0 to 2, including 0. It's very important that you include 0 here. All right, find the distance the particle travels in the time from 0 to 3. Okay, so the best way to handle this is to create a graph of position here. So I need my starting position when t is 0. So my curve is y equal t cubed minus 12t plus 3. At time 0, my position is 3. So I'm going to start at y equal to 3. And honestly, I should write this up and down since I said the values were up and down here, right? All right, so here's the y-axis, and we know that the point starts at y equal to 3, and I want to figure out what it does from there. This is at time equal to 0. So where does it go from there? Well, I know its velocity is initially negative, which means it goes down until it reaches time 2. So I'm going to think of the problem this way. The particle moves down until it hits time 2, and then it starts to go back up, and it doesn't change from then on. So at time 2, it's going to switch and turn around, and then it's going to continue on until it hits whatever time 3 its value is. Now I know its y value initially is 3. What is its y value at time 2? So at time 2, the y value is 8 minus 24 is negative 16 plus 3 is negative 13. So my y value here is negative 13. Once again, not really to scale here. What is it at 3? So 3 cubed is 27 minus 36. 27 minus 36 is negative 9. Negative 9 plus 3. Negative 9 plus 3 is negative 6. So I didn't have a great initial drawing of this. So y equal negative 6 and y equal to 3. All right, so we started here at t equal to 0. We went all the way down to negative 13 by time 2, and then we've come back by time 3 to negative 6. All right, time 3, not negative 3. All right, so this is the path that the particle takes. It starts moving down, then it starts moving up after time 2, and by time 3, it's at negative 6. So I want to find the distance that the particle travels. The distance, okay? So remember the difference between these two. The distance is the absolute value of y at time 0 minus y at time 2, plus the additional distance it traveled from time 2 to time 3. We know from time 0 to time 2, it traveled a total distance of 3, negative 13. That's a total distance of 16. And then from time 2 to time 3, it goes from negative 13 to negative 6, which is a distance of 7. And so 16 plus 7 is 23. So 23 units have been traveled in the first 3 seconds. Contrast that with the displacement, which is the difference in where it started and where it ended. There's a displacement here of 9. We started at 3, we ended at -6, so the displacement for this problem is only 9. Okay, when is the particle speeding up? When is it slowing down? Remember, speeding up is when the acceleration and velocity agree in sign. So this is the importance of this sign map. Where do acceleration and velocity have the same sign? They have the same sign from 2, not including 2 and on, because they're both positive there. They disagree from 0 to they disagree from 0 to 2, including 0 and 2, because this one's negative, this one's 0, this one's 0, this one's positive. So 0 to 2 they disagree, 2 onward they agree. So it's speeding up where they agree, which is t greater than 2, and they're slowing down on the interval where they disagree, which is the interval from 0 to 2. So v of t, a of t have the same sign. V of t and a of t have different signs. Okay, so that is a position, acceleration, velocity kind of question, like you might see on the exam. All right, one last example to get to for this review, and then we'll call it a day. Related rates problems. There are many different related rates problems that I could write down here. We've done many examples in class, and there are many more that you could be doing on the homework, which is due this weekend. Highly recommend you do that homework before the exam, as well as the example on the quiz, the practice quiz. You're going to see a related rates problem. It's probably going to be similar to one you've already seen because we've seen a lot of them at this point. This is an example kind of unlike one we've seen so far, which is why I wanted to do it. So suppose a plane is flying directly away from you. So we're here, plane, do my best, plane. Something like that. All right, that's my best attempt at a plane. So the plane is flying away from you at a rate of 500 miles per hour. How fast is the plane's distance from you increasing at the moment the plane is flying over a point on the ground 4 miles away from you? Okay, so if I draw a line here and a point down to the ground, this forms a right triangle with the ground, and then this value here is changing. This creates a triangle, a right triangle. The idea here is, I'll call this distance x, I'll call this distance y, and I'll call this distance, I'll just call it d for distance. So d is the distance to the plane, which is what we want to figure out. Y is the vertical height. They tell us it's an altitude of 3 miles. So that part's not changing. The altitude of the plane, I'm assuming, is not changing. So even though this distance d is changing as the plane flies away from you, the distance x is also changing as the plane flies away from you. Y is not changing. So I'm just going to lock it in at 3. X is a function of time. D is a function of time. They are both changing over time. And there's nothing in the problem to indicate this angle is important, so I'm going to leave it out for now. All right, so what we have here is a right triangle. Let me draw the triangle real quick. So what we have here is a right triangle of sides 3, x of t, and d of t. All right, so that's step 1. I've drawn a picture. I've labeled everything. Step 2, you have to list the rate that you want to find and the rate that you are given. So I want to know how fast is the plane's distance from you increasing. So I want to know the rate of change. Oh, maybe I should use something other than lowercase d. Let's do A for airplane. So we'll do A of t for airplane here. So I want to know dA dt at a specific point. I want to know it when the distance from me to where the plane is overhead, when this distance is 4 miles. So I want to know dA dt when x is 4. And we are told dx dt is 500. Both of those are positive because both of these will be positive because the length of a and the length of x are both getting larger over time. So they are increasing functions. All right, so step 3. Let's find a way to relate a and x, right triangle. So the most obvious way is Pythagorean theorem. So x squared plus 3 squared equals a squared. Then you should take the derivative implicitly. So I'm going to take the derivative with respect to time of both sides. So the derivative of x squared is 2x. The derivative of 9 is 0. The derivative of, I gotta be careful. The derivative of x squared is 2x, but with respect to time, you've got to multiply by the inner function x prime. Or I probably should just say dx dt. All right, and then the derivative of 9 is 0. The derivative of a squared is 2a times chain rule. And then step 5, plug in the values you know, solve for the value you want. So I know that dx dt here is 500. I know x is 4, right? Because I'm looking at this when x is 4. And I know a, on this triangle, if x is 4, then I know a is 5 because it's a 3, 4, 5 triangle. So I think I have all the values I need. So plugging in the values, 2 times x is 4, dx dt is 500, a is 5, and dA dt when x is 4 is what I want to find. So on the left-hand side, you've got 8 times 5 is 4,000. And on the right-hand side, you've got 10 times dA dt. So dividing by 10, you're going to have 400 is equal to dA dt when x is 4. Let's be careful about the units here. The units for the distance to the airplane would be in miles. So this is increasing at a rate of 400 miles per hour. Not bad. So that distance is actually decreasing at less of a speed than is the horizontal distance along the ground there. All right. So that completes the related rates example. You're going to have to do other problems like this on the exam. I could have gone over more problems with you here today, but honestly, at the end of the day, this exam completely revolves around your ability to take derivatives. You really need to be good at taking derivatives. I'm giving you a sheet of paper to put formulas on. Put the formulas on there that you need to feel good about for this exam. And work from those, things like quotient rule, product rule, things like that. But if you have any questions over the weekend as you're getting into this, please let me know. And the exam will be Monday. Find you a 3-hour period of time. Take the exam. Give yourself plenty of time to upload things. So don't work until 2 hours and 45 minutes. You've got 15 minutes left to upload everything. Make sure that you're uploading answers to questions as you come across them, okay? Make sure you give yourself plenty of time. The exam is only meant to be a 60 to 90 minute exam, so there's an extra hour and a half of time in there meant solely for you to be able to upload stuff, to make sure that you can figure out a good time for you to do all this. All right, I hope you all are having a good day. I'll talk to you soon. Bye.